And we have no way out of running. Sorry. No. All right. Let's see what we did. Do I forget to save? Yeah. Test still fails. So we two things. We need to implement. We need to generate a goal from our state machine. We also need to implement a little PID. Preference on which one first? Goal. Okay. Let's start in. So how would you do this?
If you're disabled, you probably just want to return 0 volts, right?
Yep.
You can just have that in exposure.
Okay. That one was easy though. It's not the hard part.
So you want to keep in your loop until position equals start.
But we don't have starting position here because we're on the robot. So all we get is we get the encoder, limit trigger. It's going to start at 0 because this is relative to where this robot started.
Would you want to go through the different possible numbers of the goal and see if the limit gets triggered, like 1, 2, 3, 4, 5?
Yeah, we slowly work it up. So we need I think we need another state variable because I don't think the user told us to go here, whatever they call set goal. I don't think we want to go to change time or 0. I think we want to save that. So I like to call this filtered goal. This represents, we went through our state machine and it was a raw goal and now it's a filtered goal. We did something to it. So what do we do here? Okay, so if we captured the current, we want to capture where we started. So we start here, because we don't want to then tell it to jump. We want to tell it to start where you are and then slowly move it. Okay. We can't do a for loop here because this has to return immediately. If we look at it's a good question though. If we look at our simulation here, we have to generate a value, return, and then time elapses. So we can't take time in our function. So a for loop would take time, or try to take time and fail.
Can you just give it some constant that you go up and see if it sees it?
There's a lot of friction. This one gets stuck. I think we want to feel a little more control.
We just kind of make it bold,
Yeah.
very small above where we're coming up.
Let's move it in a controlled fashion, but so we want to take our filtered goal here. So we can start by saying go where we currently are, and then every loop through here, then we can go move where we want to be up a little bit. Okay? So say start at the bottom, go a little bit every cycle. So conveniently, we have a lovely constant here, zeroing velocity. So what do we got to add? What do we need to add every cycle to go up with velocity? Zeroing velocity. Anybody? Yeah. Times, right? Okay. sense, what we're doing here? It's really quiet. Yes? So I conveniently, probably multiple years ago now, since I've been this workshop a couple times, defined a couple constants that I think are useful. Okay, these are numbers that I picked that I think are indicative of the hardware. So dt, this is this is the amount of time that elapses per cycle, which is 1 over the hertz. Zeroing velocity is a number in meters per second that I've picked. I think we should meet zero by moving at 5 centimeters a second. And also by making this a constant, when we turn it on the first time, we can move, make all these numbers really slow and safe so it doesn't race away from us. And then the other one is max height and min height. So this is, I think these are a little conservative on this hardware, but we don't need to push the limits. These tell us like how high up and how far down can we go. And then max voltage, this is the max voltage we can apply. And then I firmly believe that when you don't know where you are, you shouldn't apply full voltage. So we have a separate constant for how much voltage we should apply while we're zeroing. So these let us say when we turn it on the first time, I don't want to give it all of the power. I'm kind of scared. So we're going to turn it on very carefully and slowly. Does that help? Awesome. Okay, so we got a filter control. So let's write a little PID loop. So I don't think we need to use integral on this robot. Oh, sorry.
Could you explain quickly why filter pole is the current inflow value when you're stable?
Let me flip the question around. What do we want it to be right as we start our slow move?
What we want it to
So say it was turned on here, we lifted it to here, we enabled the robot. So this is going to read, say, 0.6 as our encoder. Where do we want it to tell it to go right as we enable it? Sorry.
When you're first enabled, it shouldn't be
Yeah, we don't want to jump. We just want to start where we currently are. And that's what that statement says. So we can do it, well, we can do it on enabled, so on the edge, or we could do it all the time. It's really just, it needs to be right when you start zeroing. And then here, then we can slowly start to move in. We can actually look for this in our tests. We'll generate some plots here and see how it's going. Okay. Let's go right under control. So I'm going to argue, I don't think we need integral on this. If the box is a ½ inch low, doesn't matter, you just shift the goal up a little bit. We don't need to be super precise. I think that's a reasonable place to start. If that is not true, we can make it more complicated. But one of the things with controls is the simpler you can get away with, the better. So we're going to start there. So we'll just do a PD loop.
And the units are okay, the voltmeter.
Yep. Oh, dimensional analysis helps you there. So errors in meters, volts is in volts, so it has to be in volts per meter. And,
What's key?
it's the derivative constant of the PID loop. So we're going to take, actually cool, you can find mechanical analogs for all this. So we have Kp times our error. So this is going to generate a force proportional to the distance. So what's a physical thing that we use that is a force proportional to the distance? Perfect. So this is a software spring. And then this is a force proportional to the velocity. So these are a little less common. Yeah, it's a damper. So this is like if you move your hand through water, it gets harder and harder as you go faster and faster. The water is not very linear, but you can find mechanical things like, well, door closer springs are dash pots. So we're writing software to simulate mechanical systems. It's actually kind of cool. Okay, I'm realizing, actually, let's make some numbers up. Anyone got a proposed KP?
10.
10? 1? We'll go with 1. And a KD. I have no clue what the right answer is, so we gotta go simulate it. 0? Great. Well, let's say for test pass sake. Oh. Oh, no, this needs to be filtered. Still fails. Can anyone see what's wrong, or should we start trying to plot and print things out?
Do you ever set it? Do you ever set it?
Yeah.
The elevator to the voltage?
I think we do. Okay. Anything else we can think to check?
Well, you never do anything after you zero.
Oh, whoops, yeah. Okay, what should we put in here?
Probably filter goal is goal.
Passed.
I think that should have passed.
What?
I don't think that should have passed.
Okay, so that's always interesting. So let's, we should figure out how to test this, or how to show what's going on a little more. So I think it would be worthwhile to figure out how to get a plot node. Okay. So I'm going to cheat aggressively. So we're going to just generate a CSV file with values in it, and we can plot that pretty quickly. I guess we should go for velocity one here too. Let's see. Wow. Surprise. Sweet. Got some data. Okay. All right, well, this is the voltage as a function of time. So let's look at this, let's get position in there. Yeah, voltage position. A little oscillatory. It actually moves. That's cool.
Huh.
Surprised?
No, it's just, I've never seen someone like simulate data and then graph it. It's kind of interesting.
Yeah, this is, I really enjoy this. This is how we do 971 robots. And this is the only reason they work is because we do this. Now, they're a little more complicated than an elevator, but all the concepts apply. So let's, I'm going to resist the urge to tune it. So I think we can break it by starting not at 0. Does that work? So if when we change the starting position, the encoder should read 0. Yep,
Would this cause like a race condition if you were to execute tests in parallel?
but we don't.
Okay, I thought it did by default.
Nope.
Okay.
There are mechanisms to, okay, a little off topic. There are mechanisms to do test sharding. So that will support taking this individual test case that we've written here and running each test case in a separate process in parallel.
Okay.
But we tend to shard on the test case level, not inside each test, because that gets really scary. And adds race conditions, which we really don't want. Okay. So we move the starting position. So say we set it to start at point 1, and then we move the current position so that way here returns 0 again. I think this has the right behavior. So let's try starting at, well, we need to start below it, so we're going to go up. Start at minus 0.1. Work. Test failed. Okay, good. That's what we were expecting. Okay, well, let's plot it. Okay. Is that really what we want to do? Not really. So what do we want to try changing? Anyone see what went wrong?
There are sudden changes in velocity, like even though we're really close, even though we're really,
Sorry, I haven't plotted velocity yet.
even though we're really close to where we need to be, it's not proportional. Like, choose voltage decrease as we get near.
So
we
I,
don't get like this
are you talking about right here?
Mhm.
I think this is when we actually zero.
I think the issue is with the built-in position and X position. I think in there, it was going to start running state.
Okay, can you just describe it in a little more broad terms what we're doing wrong?
I think when you redefine the built-in position, you're creating here. I'm not exactly sure exactly what it was, but
Okay.
or the built-in goal.
So this is not taking into account that the encoder is, that 0 is not 0 on the encoder.
Yeah. Yeah.
I want to plot something to show your point though before we get into that. So let's add the state so we can tell when it goes from disabled to zeroing to running. Just add this in. Sure. I did figure it out. Probably missed something else. Yeah, forgot to expose it. 1, 2, 3, 4, 5. Yeah, there we go. So we can see here, this is when we zero. That's when we have to jump. That's as expected, but still not. We still didn't really go where we wanted, so we have some problems. So what you were pointing out, when we go into running, we're assuming that so our control loop goes to filter goal minus encoder, and this just passes through whatever our user asked. So if 0 on our encoder is not 0, the actual robot 0 will go to the wrong place. So we need to start adjusting this stuff here. Does that make sense? Okay. Someone have a proposal for how we can modify our code to do that? Anyone?
Can add a zeroing offset.
Okay. And then how would we use that? How would we set it and make it useful?
Yeah, so when the limit is triggered, you want to set the offset to the current red position and then you subtract that from all future items.
I'll do almost what you said, but I like to flip it. I like to add offset. It just fits in my head better for some reason. And then, so down here, you're saying we add it? Like a proposal?
I mean, personally, I would put it in the filter goal, but like, that's just me, so.
So I'm gonna,
No, never mind, yeah, you're right.
I hear you, but what I'd like to do it here, I'll describe
That
why.
actually does make more sense to put it there.
Yeah, because what we want to do is, from our picture here, this goal should be in meters.
Right.
This should be in nice, real, absolute coordinates. And then we want to kind of have as much of our software working in nice, reasonable, sanitized, cleaned up units as possible, and isolate the little weirdnesses of like our encoder to as small a corner as possible. So I'd like to put it down in the bottom for that reason. But yes, we could implement it that other way, and that would work fine. Yep. Jeez, so needy. Okay.
Could you explain the offset a little more?
Yep. Hang on, let me finish. Okay, so the problem we're trying to solve is our encoder is not in absolute coordinates. So it's going to read 0 wherever we started. And then, but what we want to do is we want to compensate our encoder to get it in nice absolute units. So we need a number that is, where am I in absolute units after I hit 0? Okay. So we need to store, it's going to be a linear, just an offset, a number to add or subtract. So we need to put that somewhere. So I'm creating a variable for that. So the goal is this is relative to your starting point, and then this makes it so that this puts in absolute coordinates. So this quantity here is now your absolute location of your elevator calibrated. And then we now need to go figure out where that is. So lucky for us, we're going to define it so the edge is at 0. We could change this so the 0 is somewhere else. So that means that we want to have our current position plus offset equal to 0 and we're calibrated, so we set it as minus 0. That work? Okay. Failed. Okay. Plot. Oh, hey, we're getting close. So we were 0.008 off rather than 0.005. So that's actually pretty cool. So can we scale state? Let's do that. Yeah, so we're starting to get there, we're just not converged. So we need to tune our control loop a little bit. I think it should be a little more aggressive. We're asking for 0.05 volts. That tends not to move things on real systems. So let's scale it by a factor of 10. We got that. What?
Wouldn't you have to decrease the voltage with this oscillation?
KP decrease. It's actually the flip. We need to add damping. They're equivalent statements. We don't have any damping in our system right now. But it's also too slow. Fix that. So let's go add some damping. We're starting to settle up. Actually, though, we have this interesting artifact here. We should figure that one out at some point. There we go. I think we should find this one. A robot all of a sudden asks for 100 volts. So there's two things wrong with that. First of all, is 100 volts possible?
No.
Okay, so that's a bug, which actually means we should write a test case to catch it. So let's go. How are we going to write a test to make sure that we never ask for 100 volts? Test. How are we going to write the test to check it? So we should technically be failing our test cases if we're asking for 100 volts. Someone over here? You guys have been really quiet. Anyone? Okay, where would we want to put that? Okay. Whenever somebody asks us to simulate, we can do. I'm going to be a little cute because I don't like typing. If it's within 12 volts of 0, I'll call it a success. Okay, so let's see if our test fails. Oh, good, test fails. Okay, we asked for 101 volts. Not acceptable. So now we should go figure out why our software is asking for 101 volts. What's going on? Right on our state transition. We got something wrong there. Yep.
When you zero, your position changes really fast, so your velocity and air is going
So we need to fix that. Okay. Yeah. That sound right? Sound right? Where is it?
You just set it to 0.
So what's
Set
that?
last air to 0.
We can try that. Still got 106.
Set it to minus air, or I guess air.
Air is not available up here from the last cycle. That passed. Not sure why, but that worked. Let's go. Let's see if we can figure out what's happening. We just get lucky. scale state back down. I got the outlier down. Well, so that's still not super clean. It just happened, the wiggle happened to be within 12. Okay. That's pretty wrong. Anyone got any hypotheses?
When you did last year, plus it was output, what was the result of that?
We got a 200.
Oh, is it going the wrong way? Should we just subtract from that?
We can try that. Looks like there's something else still wrong. Oh, that worked for the same reason that encoder worked. Yeah.
So since our new error is basically going to be like filtered goal minus codec offset, if you set last error to that, then it should be the same. So velocity or like the change in time over error should be 0. The change of error over time. Right? I think you can just set it to the same expression for error.
Potentially, I like to think what's going on is since we're jumping our goal, there's a large error velocity here, so we might just need to rephrase our D term and ignore the motion. We should set a last error. Should make it. That'll actually. That might fix it.
We do last year.
So last encoder is error, or last encoder is encoder?
Oh, did I screw that up? No. Good call. Thank you. I think we had a problem.
You still have last encoder is error.
Oh, shoot. Thank you. Yes. Great. And the beauty was we didn't break any hardware through all this. Okay, this looks a lot better, I would argue. I feel really comfortable trying that. Okay. Sorry, for 10 volts per meter. This is definitely not stiff enough. Because if we think about it, so we're about 1 meter down, so we're going to apply full battery voltage at the bottom, and when we get halfway up, we're going to be up to half power, and we're going to go down from there. So it's kind of weak, I would say. I don't think we're going to get very close. Just stiffen our loop up a little bit. Just we could try it right now, but I don't know if we're going to get close to our set point. So let's crank that a bit further. We got some overshoot.
So when you're tuning a pitch do a simulation, do you normally just try to make it ideal with the simulation and then, so that when you actually test it?
We gotta look at what it's trying to do and make sure it makes sense. This is starting to freak me out a little bit. So it's making a large amount of corrections. Like, this doesn't look very smooth.
Yeah.
We're continually second guessing and changing. Real hardware isn't as good as our simulation. It's gonna do a little bit less of what we want, so we're gonna amplify the noise. So I don't know if that'd be stable. I wouldn't try that. So we should slow it down, figure out why it's trying to do that. Probably means slow KP down a little bit. Is that? That's still pretty aggressive. Not crazy. Okay. I think we should back it off a little more. Do people here know what a time constant means in relation to controls? Is that word coming? See the notes, that's right. So a time constant, you're trying to get a characteristic amount of time that something's going to decay in. So you're trying to get a time that's useful. So the time constant, the technical definition is to get to 1 over e, the 2.8 number. It's 1 over e closer to your goal. So we can look at it, takes about from there to there to get to 1 over e of our goal. If we slow it down, we're going to get a longer time constant. It's just going to take longer to converge. It's going to be less aggressive. If we speed it up, we'll get a shorter time constant. So on FRC robots, I try not to target anything over like 10 hertz for a time constant, so a tenth of a second, without a lot of justification. So here we're on the edge of, this is a tenth of a second, so we're starting to operate a little bit inside that. So that feels a little aggressive to me, at least as a starting point. If we back that up a little bit. That seems reasonable. Oh, sorry. I think I need to look at position time constant, not voltage. Okay, yeah, that's much more safe. So we can crank it back up. Okay, so we're down to the time constant of 0.2 seconds. 0.25 seconds for time constant. That's the same place to start here. Okay.
Currently, we're not having a voltage below 0.
Yeah, so let's break it. So what if we try and go further? Just fails. So we asked for 17 volts and then 13 volts. So we should probably fix that. Simple fix would be
Just max your voltage at 12. And we should do the same.
actually, we almost messed up. We have two constants, max voltage and max zeroing voltage.
So, be 12 or something.
But we should write a test too. So we want to write a test case so that we verify we're zeroing. So we have a handy max zeroing voltage we can use. Otherwise, we get our max voltage. And then we should go that work? Okay. So the test should pass. All right, test pass. That's progress. Okay, so probably there's a couple more tests we should probably write. We got the basic functionality working, which is pretty cool. Anyone think of anything else we would want to test before we put this on real hardware? Make sure we got it right. Anyone back there? What else? So we tested it to zeros normally. There's something else we could do here to try and break it that we should test.
Max height.
Max height? How about we do worse than that? How about we ask it to go to 100 meters up? How about we ask it to go through the ceiling? Past the limit. You said max height, I'm gonna go further. Set goal, let's do 100.0. Okay.
That's 1,000.
Oh, did
She said.
Yeah, I can't speak. Okay, what should our success criteria be? Sure. So if our test passes, where should the elevator be? Position should be near what? So this goal is going to evaluate to 100 because that's what we set it to. But if our elevator managed to go to 100 meters, I would declare that a failure. So what would the success be?
If it's at its maximum.
Perfect. We have a max height here. Okay. We should also modify our simulate time function to check this. Does that make sense? And should we do it in the outer loop or the inner loop? Somebody said something.
Inner loop.
Inner loop. Okay. So that would get us more. It would be more precise. So if it went over for a little bit, we catch it. Okay. Let's try it. It kept going. I don't think that's a pass. We're at 50 meters and counting. I was like, oh no, we stopped before we got to 100. Okay. Yeah, so we got a bug. It's a good test. So, how do we want to change our code here? Make this pass.
You'd say like if your goal is above the max height, then set it to the max height.
Perfect. I love it. Probably do the mid while we're at it. Okay, let's try it. Anyone see what's happening? For how small over?
0.0064.
Yeah, less than the width of a human hair. So so what should we change to fix this?
Make it try to go slightly below.
Or speak up, can't hear you.
Maybe have it try to go slightly below max height.
Okay. Yeah. So I like to, the concept I like to use here is we have a hard stop and a soft stop. So the soft stop is the max you'll let it go in software, and the hard stop is where the physical limit is. And you make them a little bit apart. So like 2 centimeters, 1 centimeter, that seems reasonable. What did you pick?
Sure. That's
Okay. Okay, we should adjust our test here. Okay. Ah, passed. Sweet. Progress. Okay, I'm gonna copy and paste this. We're gonna do the too low one. Ah, good, we got it right. Okay, yeah.
So, when did you start above the sensor?
So there's 2 answers to that. On this robot, it's going to go up until it hits the limit. And since we're at low voltage, I don't think it'll actually hurt it. It's not the end of the world. On 971 robots, we actually try and design it so the limit sensor, this homing sensor, is at a place where you can't go past it. So you always know which side you're on, and you can always go towards it. So I would probably want to fix this in hardware if we were to actually want to do it for real. But this is not my robot, so I can't change the hardware. So yeah, we just have to be very careful when we turn the robot on. We're never above the limit. But it's a very good question. Can anyone think of anything else we want to test before we go try this for real? So we've covered what happens if we don't start at 0. We don't start at a 0 point. We've tried going too high. We've tried going too low. We've done some control loop tuning.
Hi, I'm Sarah Koenig.
We verified that it respects the max and min voltages. Not coming up with anything else here. So before we move on, I'll mention there's some cool things we can do here. Say somebody wanted to figure out what's going to happen if an encoder got unplugged. We could just go write a simulation, right? Actually, wouldn't be that hard. And then we could go figure it out in software and then potentially work on detecting it. So a bunch of kind of cool stuff we can do like that. Okay, are we ready to try this for real then? I'm a little nervous. Okay, that's good. So let's walk through the or the bring up process here. I really don't want to break this robot. So the first thing we're going to do is we're going to confirm that all of our sensors and motors work as we expect. Because one of the most common things is if the motor is plugged in backwards, so it goes down when you ask it to go up, you're not going to go very well. Other failure modes, so that's the first one. And then the next thing we're going to do is we're going to turn everything really far down. So if you start with like 2 volts, 0.1 PWM, it's barely going to break friction. So we should be able to tell if it's doing something reasonable at that point. And then the other thing we can do there is we can turn our zeroing speed down. We can make it go really slow, so it can't go very fast. It doesn't have any power. So that way we can watch it work on the hardware for the first time and make sure it looks reasonable before we then go let it loose. Okay, so let's do it.
Have you actually run this or is it the first time?
Never run it.
Oh, that's great.
Unlike some of the other robots I've done this with, I got all the sensors working 5 minutes before class. This is brand new. So we will do this very carefully. Oh, let me walk you through. So this is the code that we've got to actually implement hardware. So I didn't use very much WPLI, but essentially we have this this call here. We sleep. Oh, we didn't test what happens if you're disabled. We should test that. If you start disabled. But let's finish this thought. So we wait, and then we call iterate loop. We repeat that over and over. So that's very similar to our simulation, where we simulated time elapsing, and then we ran. So iterate loop. We got some test code in here. So it calls loop.update, just like our simulation did, feeds it in the encoder, which I've gone and I counted the gear teeth and I think it's the right distance. And then we have our Hall effect, and then driver station is enabled. And then we convert from volts to PWM, and then we set the tau. So we're able to keep most of our logic here in loop.update. So we can share it between our simulation and reality. And everything in here is talking about how to translate those concepts from sensors in and then from the output of that back out to the hardware. But yeah, I want to do a disabled test. We're going to start this thing disabled, not enabled. Let's go. We'll cheat aggressively. We're going to disable it. We're going to be enabled if we're past 1 second. Okay. It actually looks the same. So it waited until 1 second and then started line voltage slowly. So I think that looks good. Okay. So then we're going to start by turning it on disabled, and we're just going to print out the encoder value and the Hall effect. That's about a meter. It's actually pretty good. Okay. So we should see. Our sensor go high? Yeah, that's good. Good, so our coder looks same. So now let's, so we're gonna take, we're just gonna apply 0.1 power and we should see it go up if we got it right. This is a low enough power that if we stall it into a limit, we're not gonna hurt the robot. Let's deploy that. Can you back up? Thank you. Okay, so we're enabled. That's not quite enough power to move this one. We can up that slightly. Good. It's going up when we apply a positive. That's a good sign. Hang on, we did not turn everything down. So let's go. So we applied about so we applied 2.4 volts. So 4 volts would be fine. So we just cap everything to 4 volts when we start. That should slow it down. Let's go 10.
Do you scale your zeroing voltage at all as well, so it's still lower than max? Or is that shouldn't work?
Actually, let's slow the speed. Ready? Oh, I lowered the derivative constant. That's a high frequency noise. It's very likely coming from the derivative, because it amplifies high frequencies. So we'll back that down. Looks like our simulation was a little too perfect. It's moving.
Come on, baby.
Moving at 1 centimeter a second. We might need to speed that up. Okay, let's speed that up. Now we'll go back to our 5. Are we ready? That's all good. Sweet.
Find the button that's supposed to move.
Let's move the buttons so that they're. Let's move the buttons so they're.
Where do these operators, does it get a stick button not return?
It returns a bitmaps for all the buttons. I just went really far down in WPI Live.
Okay, I was gonna say that's interesting.
We used pretty low level primitives a couple of times. Let's double check. Yeah. Let's pull it from back out. Okay, so let's give it a little more power now. Just ease into it. Cool, it's working. All right. Anyone got any questions? All right, that's all I got.
Whenever it works, you put declare victory and go home?
Woo! Thank you, everyone.
So how does tuning so tuning other types of maybe like more complicated controllers go to the simulation?
Much more complicated. Do you?
Like commercial.
Same thing. We can do the same thing. We're baking a lot into we're trying to we're assuming our model is reasonable. So if we wanted to be better, we could do things like go into CAD, because the goal is to do this before the hardware exists. Go into CAD and go figure out how much all these components weigh. And that should give us a better model for the mass. We could then simulate a motion profile in simulation. Go plot it now. We can see exactly what it's doing. Go with our control loop.
I've tested all of this. And the biggest issue I find is how can we know that our model is accurate? And we just have to build it and just trust it. Or
you got to bootstrap it. So if we were going to be super rigorous right here, the next step we would do is we would feed motions in here. We would go capture data, and then we would go feed the same inputs into our model and go look at how well the two compare. And we tune our model with entry all the time.
And when you tune the model, that doesn't you just kind of fake the stuff that you tell it is, or do you have to?
So look here, there's two terms. We have a big long constant. These are all constants times velocity plus a big long constant times voltage. You can literally change anything in any of those, and you'll get the same effect. I like my favorite tuning knob is resistance, or I'll add an efficiency factor to try and map current to torque. I'll go through some more of the modeling stuff tomorrow. Normally I like to do the workshops in the other order, but the time slots work better this one. So yeah, you can tune parameters in there and you make it fit better. Or so this will be this is going to be your damping, and this is going to be how fast it actually goes. And they'll play out. Other questions? Yeah.
So if, more generally than just this, but if a team that has moderately sophisticated software like pathfinding, that type of stuff, wants to get to the next level of sophisticatedness, what path do you suggest that team follows?
To get to that time?
Well, no, from basic level of autonomous control and whatnot, to get to the next level of sophisticatedness with software and robot control.
This is how we do it.
Okay.
You gotta be able to, if the only way you can test your code is to go put it on a robot, drive it, and see if it did the right thing, your iteration cycles are gonna be a lot slower.
Okay.
So you can kind of tease the world into two. There's kind of your perception side, to use kind of the new hot word, buzzwords, but that's taking your sensor data and trying to figure out what's going on. So here, we're kind of, actually, this is our entire perception layer right there. It's not very exciting. We're trying to estimate how fast it's going. So you can do a lot more complicated filtering here. Say you're trying to estimate position on the field, that falls into that bucket. And then there's the control side where you're taking your estimate of where you are and reacting. So for estimation stuff, the best way to do it is to collect data and then feed your data through your algorithm over and over and over and over. And you can then corrupt your data and try and modify it and just see how it performs. And for the control side, you need to write a little simulation, start to execute it. And your simulation doesn't have to be perfect. More questions? Okay. That is the right question. Yes. Let's just turn it on.